Okay.
Very good. All right. Thanks everyone for coming to this installment of our long-range colloquium. We're really excited to have Nathalie Leon from Princeton University here. She's one of the world's leaders in work on NV centers, and as you'll see some other things as well. And lately, I won't say too much. I think the work she's been doing on diving deep into surface science to improve quantum coherence has been really great. And I'll leave it to you, Nathalie. Thank you.
All right, thanks, Val. Thanks for the invitation, and it's nice to have a chance to chat with some people beforehand too. So what I'll be talking about today is some of the work that my group has been doing on correlating surface spectroscopy with qubit measurements to improve various quantum platforms, particularly NV centers in Diamond. So I started my group, I guess 4 years ago now at Princeton, and very broadly, what we've been working on and focused on are atom-like systems in the solid state. So over the past several decades, people have done a lot of really beautiful work in quantum information processing built on trapped cold atoms. And this is because atoms really act as these excellent quantum systems that are a nice playground for a lot of this physics. They have very long spin coherence times that can be used as your quantum degree of freedom. And importantly, they have very efficient optical transitions that you can use for initializing and probing the spin. So what we're focused on is trying to realize atom-like systems in the solid state where you have all of these same advantages, but then you can imagine now trying to integrate these things into scalable devices like these integrated photonic chips. And this has a lot of opportunities for things like for applications in quantum information processing, but also quantum networks, because you have this nice interface to light. And then because you're in the solid state, you have this new opportunity open up in utilizing these defects as nanoscale sensors. So that will be the focus of my talk today. So just to give you the lay of the land, my group is roughly split into two, where half of my group is now looking at these atom-like systems in the solid state and trying to find new solid state defects for applications in quantum networks. We have a fairly large material science and spectroscopy effort to identify these systems, and then we are recently trying to integrate these things in nanophotonic devices to deploy in long-distance quantum communication. The other half of my group is trying to develop these color centers as platforms for nanoscale sensing, and this has actually taken us down this kind of rabbit hole of work in surface spectroscopy and surface analysis, and this is most of what I'll talk about today. So for the last several years, quite a few people have been working on trying to develop NV centers as nanoscale sensors. The reason that this is a really attractive system is that they have very long spin coherence times, several milliseconds at room temperature. And they also have a very convenient manifold for doing optical readout and initialization with off-resonant excitation. So this means that all of these optical initialization and readout schemes also work at room temperature. And then it turns out that the NV center also has bright enough fluorescence that you can image single NV centers. So basically what you can do is combine the many, many decades of work that people have done on understanding how to manipulate spins in electron spin resonance and NMR experiments, and combine that with the last 3 decades of single center imaging to be able to do kind of sophisticated magnetic resonance experiments at the single atom or single molecule level. So the promise of this technique is that if you look at something, just naive, like the dipolar coupling between your NV center and another spin, you can see that this dipolar coupling changes very rapidly as a function of distance, really at the angstrom or even sub-angstrom scale. So you can sort of conceptualize this NV center as having the largest possible magnetic field gradient because it really acts as a point sensor. So because of how exciting these properties are, there are a lot of people who are now developing this as a tool for looking at other systems. For example, there's been some recent work where people have shown that with some clever pulse sequences, you can even use the NV center for chemical shift resolution nuclear magnetic resonance experiments. And there are quite a few people who are integrating NV centers into scanning probe measurements to interrogate other systems like condensed matter systems. This is some really beautiful work out of Patrick Malatinsky's group from last year, where they were looking at magnetic domains in chromium triiodide. But what we'd really like to do is, these kind of single molecule experiments where you can do this imaging at the single molecule or even single atom scale. And in principle, this already works very well just with the coherence times and kind of spin readout that you can get with an NV center. So this is an example from Tim Taminiau's group from last year, where they took a single NV center and then used it to do this nanoscale magnetic resonance imaging to look at individual carbon-13 nuclei that were in the vicinity of the NV center. And here they mapped out, it's in the title of their paper, it's like 27 carbon-13 nuclei or something like that. And they made this beautiful map. And you can see that, of course, these things are separated at the sub-nanometer scale. So they've really already shown kind of this proof of principle experiment where you can do this single atom magnetic resonance imaging. Okay. So now if you would like to deploy the same kind of sets of techniques for looking at arbitrary targets rather than just looking at nuclear spins in bulk diamond, now you run into a little bit of another problem, which is that, of course, getting both your high sensitivity sensing and high resolution, both of these things require very, very close proximity, at nanometer scales to your sensing target. And bringing your NV center close to an external sensing target also means that you're going to be very close to the diamond surface. And while it's now commercially available, while there are now commercially available very high purity bulk diamond substrates, in general, mankind is sort of really bad at surfaces. And actually, in particular, we're really, really bad at diamond surfaces because diamond is the hardest material in the world. So it's actually quite hard to prepare and control this surface. So what happens is you have a bunch of defects at this uncontrolled surface. These give rise to magnetic and electric field noise, and that noise obscures the target that you're trying to see. The reason that we know this is that if you look at NV centers and just plot their spin coherence time as a function of distance away from the surface, deep in the bulk, you get T2s of something like a few milliseconds. But then as you approach the surface within about 100 nanometers, you get this precipitous decline of the spin coherence. And by the time you get to within a few nanometers of the surface, your spin coherence is more like a few hundred nanoseconds. So this is actually pretty severe scaling and a real limitation for any of these schemes to try to deploy NV centers in the single molecule imaging work. And this has been seen by, so each of these colors is a different diamond sample, so this is not very sample dependent, and this has been seen by many other groups as well. So what we embarked on was a general project of trying to understand what was going on at the surface in detail. And one of the big challenges here is that the NV center is your most sensitive probe, but it's completely non-selective. All that it tells you is, I'm seeing a noise bath, and that makes me unhappy. But it can't tell you anything about what's causing that noise bath, and it gives you very limited information other than the spectrum of the noise. The other thing, or on the flip side, there do exist a large number of surface-sensitive techniques that have been developed over the last several decades. They tend to be very challenging and low sensitivity, and maybe more fundamentally, they probe much, much larger areas than the NV center does. So a priori, it's not obvious that you can find a technique that actually gives you the relevant information for what actually is the microscopic source of noise that is limiting your NV coherence. In addition to that, there's a number of other technical problems having to do with diamond being an insulating substrate and the fact that everything has a really bad carbon background, so it's hard to differentiate between your background and looking at diamond. So what we decided to do, just sort of programmatically, was develop a series of techniques to try to study the diamond surface in detail by correlating a large number of traditional spectroscopy probes with the kind of nanoscale spectroscopy that you can do from the point of view of the NV center. And I would love to tell kind of a sexy story about how we knew exactly what we needed to do, and then did that and, figured out the microscopic mechanisms. But the truth is, I think actually the correct approach to a lot of these things is that you just have to live in a world where your average expectation value of information from a given technique is close to zero. And you just have to try a very, very large number of things to see what actually gives you, a good lead in terms of correlating with your qubit measurements. So we tried a very large number of techniques. This is a partial list. Everything that's in gray is actually stuff that are actually techniques that didn't really give us useful information. In the end, the kind of three main workhorse techniques that I'll talk about in this talk largely are XPS, UPS, and NEXAFS. So you just have this alphabet soup, but in general, your surface sensitivity comes from something like the short inelastic mean free path of electrons as they get ejected out of the material. So you only look at the top few nanometers of material. In addition to these kind of surface sensitive probes, we can do something a little bit more sophisticated than just asking the NV center whether or not it's happy, which is driving the NV center with different pulse sequences to try to learn something about the spectrum of the noise bath. So for example, you can do these different dynamical decoupling sequences that push out the NV coherence, and then you can just do a Fourier transform of that to get a spectral decomposition of the noise. So one of the things that we learned sort of immediately in this project was that a lot of the community talks about how they prepare oxygen terminated surfaces because these are good for NV charge state stability. But what we discovered is that there are many different types of oxygen terminated surfaces. And even if you have the same nominal oxygen terminated surface, you can have really different electronic characteristics based on the surface morphology. The reason that this is especially critical for diamond is that diamond actually has highly hysteretic processing. So if you, for example, process a diamond in oxygen, it will etch the 111 facets much faster than the 100 facets. So any small amount of surface roughness will run away and give you really drastic morphological differences. So these are two surfaces that started out with just slightly different RMS surface roughnesses from polishing that just differed by about a factor of 2. But after a couple of processing steps, you can see that the one with higher surface roughness really looks quite terrible. And then if we look in near-edge X-ray absorption fine structure spectroscopy, which is a probe of the density of unoccupied states, we can see that there's very different electronic characteristics for this rough surface. So what you're looking at here is the unoccupied states. So everything that is to the right of this kind of exciton peak is the conduction band structure in diamond, and everything that's to the left shouldn't be there because it's a mid-gap defect state. And this rough surface has this giant kind of forest of mid-gap states that have to do with, that are entirely just related to this morphology. So what we discovered is that in order to really control this surface morphology, what we had to do was really avoid any contamination at the surface at every single processing step. And then to deal with the fact that diamond is such a hard material, we had to do iterative processing to basically remove the damage that was done from the previous step, and then iterate through that until we could get to a very smooth surface that we could control. So without going into too much detail, what this process generally looks like is we start with very high quality polishing. We can do reactive ion etching to remove the subsurface damage from polishing. That leaves behind some RIE damage, like implanted chlorine ions. So then we have to do some further RIE to remove that damaged layer, some thermal annealing to intentionally graphitize the top few nanometers of material. And then finally, we can do a chemical anneal to actually fix the chemical termination of the surface. What we were able to see immediately just from doing this very long sequence is that we're able to get NV centers with coherence times that are better by almost a factor of 10 for the same depths. So all of these points are what I showed you earlier, whereas these dark green points are kind of our typical best NV centers from all of this processing. So if you don't want to hear anything about surface spectroscopy, you can just turn off your video and fall asleep for the next roughly 20 minutes. while I go through the detailed story of understanding what actually happened here. But the takeaway message is that we're able to really improve, basically use the surface spectroscopy to improve the coherence times of these shallow NV centers. So to try to understand and disentangle some of what's going on, we can kind of zoom in on these last two steps and compare NV centers under this surface with NV centers under this surface. And I'll refer to these as the annealed and acid clean surface and the oxygen annealed surface. So if we just compare NV centers between these two last steps, we see that the Hahn-Echo coherence time gets extended by a factor of a few. This is on a log scale, so this is actually a big change. And then again, we can apply this dynamical decoupling to probe what happens to the noise at higher frequencies. And what we find is that the coherence time is enhanced for this oxygen annealed surface for every single kind of number of pulses that we use. And then very importantly, before we do this oxygen annealing, the acid clean surface gives us these NVs that have a saturating coherence time with number of pulses. So you were not going to be able to get away from this noise bath just by applying more and more pulses, whereas we don't actually see any saturation under these better surfaces. We can also do a different type of spectroscopy of the bath by taking advantage of the fact that the NV center is a spin 1 system and looking at just spin lattice relaxation. And specifically, we can look at spin lattice relaxation between the ms equals -1 and 0 states, which is a single quantum transition. And then we can also look at relaxation between ms equals -1 and ms equals +1, which is a so-called double quantum transition. This is a little bit of an oversimplification, but in general, magnetic noise can drive these single quantum transitions, but not the double quantum transition. So this double quantum T1 is more sensitive to electric field noise. And what we see is that between these two surfaces, we see a very large change in the single quantum T1 and a very small change in the double quantum T1, which indicates that this change in noise is predominantly magnetic. Putting everything together, we can do spectral decomposition of this NV decoherence and then sort of plot what the spectrum of the noise looks like, and then put these single points in for our single and double quantum experiments as well. The dashed line is 1/f scaling for electric field noise so that you can actually compare these things directly. And we see that indeed it does look like we're dominated by magnetic noise over all of the relevant frequency range, and that this is a very white noise bath. So it looks like we're dealing with very broadband noise, even after we've done this last oxygen annealing step. Okay, so that is what we can see from the point of view of the NV center. And now we can look at surface spectroscopy to also see what the differences between these surfaces are. So again, this is near edge X-ray absorption fine structure spectroscopy. Here, instead of the carbon edge, we can look at the oxygen edge to figure out what's going on with the chemical species at the surface. And actually what we see is that before and after this oxygen annealing, these NEXAFS spectra are broadly similar. I think a real surface spectroscopist would be really mad at me for saying that, but what I would say is that I see a peak here and then kind of a bump over here, and that's basically the same after you do this oxygen annealing. But the major difference is that after the oxygen annealing, you can see that there's a dramatic polarization dependence. So as I rotate the orientation of the sample relative to this polarized X-ray beam, you see that these features change drastically, whereas they don't for the acid clean surface. And what this indicates is that the bonds are highly ordered in this oxygen annealed surface, which is why you can actually see this polarization dependence. So our general kind of microscopic model for what the surface looks like, this is obviously a dramatized depiction, but is that in the acid clean surface, we have a lot of disorder at the surface. So these bonds are sort of pointing in many directions, whereas in the oxygen annealed surface, we have mostly ordered rows of ethers. But we actually don't expect there to be a very significant chemical difference other than this degree of disorder. The other consequence of this disorder is that if we do ultraviolet photoelectron spectroscopy, which is a probe of the occupied states, what we actually see is this very large difference in the electron affinity between these two different surfaces, which is very surprising because the oxygen coverage is pretty similar. And actually, while we were doing this, we solved a log standing puzzle that not very many people cared about, but 7 people cared about really, really deeply in the community, which was that if you calculated the electron affinity expected for hydrogen terminated diamond and you measured it, you basically got the right thing. But for oxygen terminated diamond, you got this anomalously small electron affinity, and it wasn't really understood why these calculations were so poor. So I think what we realized is that actually this 2.1 eV is very close to the calculated value. And essentially this disorder at the surface gives you a large number of electronic defects that suppress the electron affinity. Okay, this is maybe for the specialists, but we can also do a large number of different types of surface spectroscopy to convince ourselves what the actual chemical termination is. And we believe that it's predominantly ether terminated, about 80 to 90%. Okay, so now with all of this exquisite control over the surface, what we discovered is that the surface termination is actually completely reversible and reproducible. So here is an NV center at 7.5 nanometers with a spin echo coherence time of around 10 microseconds. We can do this final oxygen annealing step to enhance the coherence time. And then we can thermally reset the surface and we see the coherence time drop again. And then we can do a final oxygen anneal to bring the coherence time back. And we basically see that this is true for every NV center that we look at in the sample. So we're really just monkeying around with this last layer of atoms at the surface. This would only be possible if you have very good control over the surface contamination. So just to conclude this first part of the talk, we've been able to use this, this feedback loop between surface spectroscopy and NV-based spectroscopy to figure out how to make a new diamond surface termination with a highly ordered ether termination and very, very smooth surface morphology. This allows us to make NV centers within a few nanometers of the surface with coherence times that we can dynamically decouple out to about 100 microseconds. And this really relied on identifying failure modes with surface spectroscopy that had to do with maintaining careful control over the purity and the morphology. And much more broadly, I think, what we've shown is that using these complementary spectroscopy techniques allows you to discover these sources of noise and systematically eliminate them. Okay, so
Nathalie, I think we have a question in the audience.
Oh yeah,
from Babak.
Yeah, could you just, I think I missed this early on, how does the depth play into coherence time? And I see that, like you have this longer, after these corrections for the highest depths that you have, you kind of come back to what you started with, right? Whereas in the other ones, you end up with larger times. Anyway, so I guess those are two questions. But.
Right. So the reason that the coherence time drops as you come close to the surface is because you have magnetic noise from defects at the surface.
Okay.
So what you should see, if we went to much larger depths, which Anya Jayach's group has done with their scanning measurements, then you can see that around 100 nanometers, this sort of levels out because you're mostly just probing bulk noise at that point. So the scaling, I wouldn't bet like a limb on what the power law scaling is, but it's something like to the 4th power is what it kind of looks like. So then what we've done here is, so then you were asking, why is it that there's a large delta for the shallow NVs, but then a smaller delta for the deeper NVs? So this is because what we're doing with the surface processing is suppressing surface noise. So of course, only the shallow NVs are going to feel that difference a lot more.
Right. Okay, good. Thank you.
I think there's another raised hand.
Indeed. I hope I don't pronounce it wrong, Magesa. Or,
yes.
Yes, go ahead.
Thank you. I was wondering, are your samples exposed to ambient conditions at any time of this preparation process and transporting in between measurement techniques? And related to that, all the adsorbents that you showed, or the surface termination on one of the previous slides with the ethers and all the CNO, is that just from the air, or is that from the acid cleaning?
Yeah, that's a good question. So yes, we do transport these samples, from tool to tool and from furnace to furnace, and in particular, it basically gets exposed to air, put in liquid, exposed to air again, and all of that stuff. So most of the contamination that we've been avoiding here are the kinds of contamination that really lead to this micromasking that gives you this bad surface morphology that I showed at the very beginning of the talk. If you're actually interested in this topic, you should just email me later and I'd be willing to just send you all the stuff that we have. But one of the things that we uncovered that I think is quite general to other people who are dealing with surfaces is that there is silicon contamination that's ubiquitous from packaging and gloves and a lot of different containers because you have this high vapor pressure PDMS type substance that people use for packaging and things like that. So we really had to studiously avoid that because you can't remove it in situ at all. But sort of no matter what you do, you always have a layer of adventitious carbon that comes from the atmosphere. And we don't know to what extent that affects the final coherence time of our NV centers. But I'll talk a tiny bit at the very end about our efforts to try to do all of this stuff in UHV so that we can avoid that problem.
Thank you.
I think there was another raised hand.
Yes, Ricardo, you can unmute.
Yeah, hi. I was wondering if you have replicated this type of, say, experimental scheme with other types of surface terminations, like, say, nitrogen or fluorine?
Yeah, so the shortest answer is no, because most of these surface terminations are highly damaging. So you tend to not get good NV properties. And I'll talk a very tiny bit at the end about our attempts to make new surface terminations in ways that are less damaging. But in principle, if you had a good chemical method, then this should be, a general technique that's portable to those kinds of surface terminations. Okay, I don't see any other.
I have a question actually as well.
Sure.
Is there a easy way to know when the lab products we're buying have this contamination, this high vapor pressure silicon stuff?
So the way that we diagnosed it was that we have access to a rapid turnkey XPS system. So it's easy, but you have to have one of these systems. I mean, you could also do normal lab XPS, but that tends to be a little bit more laborious. But basically what we're looking for is contamination on the order of like I'd say 0.1% is what you can easily see with XPS. And you tend to see that from a lot of gloves, and gel packs are especially bad.
Okay, thank you.
Okay, so so what I've shown you so far is that you can correlate X-ray spectroscopy with this nanoscale spectroscopy to learn something about what's going on at the surface. But all of the nanoscale spectroscopy that I've shown you so far is very conventional. So we're just applying dynamical decoupling to the NV center and using that to do spectral decomposition of the noise. So now what I'd like to tell you about is a quick story on a slightly more sophisticated version of nanoscale spectroscopy that we think can be deployed in a large number of systems. And here, the toy system that we're working on to show these techniques is just the surface spins that we find that are defects at the surface of diamond. Okay, so this is, so our main workhorse for being able to do these, to interrogate these spins is something called double electron-electron resonance. Schematically, this is very simple. You basically do a Hahn echo sequence on the NV center that consists of, pi over 2 pulse, pi pulse, and pi over 2 pulse to read out the spin. And this should refocus dephasing from quasi-static noise in the bath. But then what we can do is bring in a second microwave tone that selectively addresses this population of surface spins which are spectrally separate from everything else because they're G equals 2 spin 1/2 electronic spins. And basically when you apply this pi pulse, what you effectively do is cancel out the noise from everything else with this Hahn echo sequence, but then you continue accumulating phase from this additional, from these other surface spins. So you isolate out the contribution of the surface spins, the decoherence of the NVs. So the way that these experiments look is this purple trace here is a Hahn echo decay curve of a single NV center. And then when we add in the second pi pulse, we get a faster decay in this red trace here. And then if we just divide these two curves, we get out a signal that is the decoherence due to these surface spins. And it's essentially like a free induction decay measurement on the NV center. So we had done these experiments for a very long time and had a very large data set from our lab over the last several years. And what you can now do is basically use these free induction decay curves to back out a Dirac coupling rate. So basically the rate at which you decay due to these Dirac spins. And we can again plot this rate as a function of depth away from the surface. And we generally see an inverse dependence where we have much higher coupling rates as we approach the surface, as you'd expect if you were addressing a bath of spins at the surface. Okay, so that's what we can see from the NV center. And then now what we want to do is figure out whether or not this correlates with any signature that we can see in surface spectroscopy. So returning to NEXAFS, we can now look at the carbon edge. And what we see is that for these two different surface preparations that I talked about earlier, the acid cleaned and oxygen annealed surfaces, if you zoom in this mid-gap region of the carbon edge NEXAFS, we could see that all of our acid clean surfaces had this little peak at 282.5 eV, which people had previously assigned to dangling bonds, sp3 dangling bonds at the diamond surface. And we also know that in general, these acid clean surfaces have much higher Dirac signals. So to show that a little bit in a more controlled way, what we can do is look at individual NV centers before and after we do this oxygen annealing, and we can look at this Dirac signal for the same NV centers. And we see that, that the Dirac signal gets suppressed by a factor of several and almost an order of magnitude for some of these NVs. Okay, so we think we have something that we can see in X-ray spectroscopy that correlates with the surface spin signal. But I already showed you a giant pile of data showing that quite a few things change when you do this oxygen annealing. So it's not actually obvious that these dangling bonds really do correspond to these spins that we can see in Dirac. So what we need is another toolkit for being able to disentangle these effects. And what we did was at Brookhaven at NSLS, we did some in situ vacuum annealing where we did X-ray spectroscopy after different after annealing at different temperatures. So we start with one of these acid clean samples, and then we anneal at 500, 650, and 800 degrees. You basically have to get to something like 800 degrees to really start pulling oxygen off of the diamond surface. But what we see is that if you zoom in on this carbon edge, after 650 degrees, this little dangling bond peak disappears. So before we've really done anything else to the diamond surface, we can selectively anneal away this dangling bond peak. And we see that after 650 degree annealing, the oxygen spectra really look basically the same. So what we think is that we have a selective annealing process for this dangling bond peak. And now again, we can go back to the NV centers and look at a sample where we've characterized this Dirac coupling across many NV centers, and we see this inverse scaling with depth. And then after we do the 650 degree vacuum annealing, we see that the Dirac signal gets suppressed by a factor of almost an order of magnitude to these purple points here. So, okay, so now this is nice because we have some handle to selectively anneal away the surface spins, and we think we have a nice signature that we can also look at in X-ray spectroscopy. So this is around where we had gotten to right before quarantine. And we were dealing with a few big puzzles in the data at the time. So the first big puzzle is that if you just extract the sort of naive model for what the density of surface spins is, given this, this set of purple points here, this corresponds to around 0.005 spins per square nanometer, which is a linear spacing of around 14 nanometers. So this means that the surface spin density is actually, or the surface spin to surface spin distance is now comparable to or much larger than the NV depths that we're looking at. So on average, your NV center is actually much closer to the surface spins than the surface spins are to each other, which means that instead of seeing this monotonic increase in Dirac coupling as you approach the surface, what you should see is a statistical spread, right? Because you should be sampling some configurations where you accidentally have a surface spin that's very close, but also configurations where you have a surface spin that's very far away. So that's sort of the first statistical puzzle. The second puzzle was that actually where a lot of this arose was that I had an intern in my group who was very dutifully taking these measurements and doing a really careful job, but then he kept on bringing me fits to the data that just fundamentally didn't make sense from everything that I understood about spin resonance. So specifically, if you just look at, if you open up Abraham and you look up what you should get for a free induction decay in a quasi-static bath, then you should get something that looks like e to the minus gamma t to the n, where n is 2. And this is, you know, very well established and very well known from the spin resonance literature. But what we were seeing kind of consistently was that if you tried to constrain the fits so that this exponent was 2, this was kind of the best fit that you could get, this orange trace here. So it's clearly not the correct shape of this free induction decay. So you can see that we have this sort of heavy-tailed distribution, which is, you know, some kind of stretched exponential decay. So one kind of, you know, one of the few nice things to come out of quarantine was that we had a lot of time to reanalyze very old data. So we went back into our historical data sets, and we were also talking to collaborators in the Lucan group, in particular, Bo Dwyer and Ilana Urbach and Dolev Blufstein, and started you know, fitting these things more carefully and convinced ourselves that indeed all of these exponents didn't make sense, and many of them were quite low. So in particular, the standard theory only predicts that this n should be between 1 and 2. You get an n of 1 if you have a perfectly white noise bath, and an n of 2 if you're in this quasi-static limit. But if we just did this fitting across all of our data sets in my group and in the Lucan group, you can see that we actually get quite a few that fit to this exponent that's below 1, and that you get lower and lower exponents as you approach the surface. So for shallower NVs, you get kind of more anomalous stretched exponential decoherence. Okay, the last kind of statistical puzzle is that coherent coupling is actually quite rare across all of these observations. So if you really had this low of a density, you should basically see a strongly coupled surface spin the vast majority of the time. But basically looking over our historical data sets and the Lucan group's historical data sets, you really only observe coherent coupling, which looks like this, where you have these, you know, oscillations because you're transferring polarization back and forth between the NV center and the surface spin. We only observe this in maybe 1% or a few percent of NV centers. And intriguingly, there are a few special NV centers where you could see a coherently coupled signal that blinks on and off in human timescales. So, you know, it shows up and then disappears after a few seconds. So all of these observations kind of led us to a model where, you know, maybe what you're seeing is not actually a static bath of spins, but many different configurations of this 2D spin bath. And then instead of being able to see this coherent coupling, you're actually just averaging over many, many decoherence curves. So one question that we had is, you know, can this kind of model explain all of our different puzzles? And indeed, if you just do this configurational averaging and just do, you know, straight numerics and, you know, Monte Carlo simulations, then what we see is that for very deep NV centers, you'll fit to an exponent that is 2. So it gives you the good naive model. But then for very shallow NV centers, what you see is this configurationally averaged 2-dimensional bath, which it does turn out actually should give you an n of 2/3. There's a term in the theory that gives you something that looks like d over 3. So for shallow NVs, we get n of 2/3. For deep NVs, we see n equals 2. And then the time at which you see this transition point, or sorry, the depth at which you see this transition point should depend roughly on the density of spins at the surface, because that sets the relevant length scale. And indeed, as you increase the density, you can see that this depth gets shallower and shallower. Okay, so those are the numerics. We can also just put together an analytical model for this dipolar coupled bath. And you get an integral that's not very easy to solve directly, but what we can do is solve it for very short times and for very long times. And in these two limits, at short times, we get, again, this nominal model of an n equals 2. And then for very long times, we do indeed get this n of 2/3. And then somewhat surprisingly, if you then just calculate sort of the results from this analytical model, what we see is not that you get a single exponential that gives you something in between these two exponents, but instead you see a crossover time. So at early times, you really have, this is now on a log plot, which is not that easy to understand, but it gives you the very nice visual feature that the slope corresponds to this exponent. So what we see is this transition between a slope of n equals 2 and a slope of n equals 2/3, and there's sort of a sharp kink in between. And this crossover time is just directly related to the depth of the NV center. So as we increase the depth, this crossover time gets pushed further and further out. Okay, so putting these kind of the numerics and the analytical model together, there's sort of a nice physically intuitive geometric interpretation of all of this, which is that the NV center, after some given time, really just senses some particular volume, right? And this volume grows with time. And because it's spatially separated from your 2D bath, there's some time delay before this sphere intersects the surface, at which point you start integrating over the area of spins at the surface. So this kink in time is just directly related to the depth of the NV center. Okay, so then now armed with this theoretical model, we could go back into the data and look for NV centers where people had oversampled their coherence significantly. And it turned out that we actually had this data for something like 4 NV centers. So here are 4 NV centers where we can see an experimental signature of this crossover time. So these are NV centers at different depths. And what we see is that indeed at early times, we have something that looks like it fits to a slope of n equals 2. And at late times, it curves over to an n of around 2/3. So everything that I told you about actually, isn't really special to NV centers at all. It's basically generic for any set of dipolar, disordered dipolar coupled spins in 2 dimensions, where you have access to sampling over many different configurations. So you need configurational averaging and you need 2D. But the key thing is, so in principle, you should be able to see all of the same physics if you just did bulk ESR in a 2D system or bulk NMR. But the key thing here is that the reason that the crossover time here is observable is because the NV center is a geometrically separable probe. So we can just set the distance from this bath arbitrarily rather than interrogating the bath directly. And if you interrogated the bath directly, this time would be set by the configuration with the closest separation between spins, which could be at lattice constant spacing. So normally this would be at inaccessibly short timescales, but here, because we can move the NV center sort of arbitrarily far away from this bath, we can now push this into experimentally accessible timescales. Okay, so this is work that we're now writing up that we did in collaboration, as I said, with the Lucan group, and then also with some theory support with and discussions with Slava Dokrovitsky. And it's kind of nice that we were able to take the time in quarantine to just look at our data more carefully and solve some of these puzzles. You know, what I've talked about is that the NV center is kind of a nice local probe of these external spin systems. If you just do very careful measurements of the decoherence, and in particular, what we've shown here is that even just looking at the stretched exponent gives you this nice probe of the dimensionality and the dynamics of this bath. In terms of the microscopic details of what we learned about surface spins, you know, we sort of showed with this probe that these surface spins are hopping around. And then again, just to emphasize this, the reason that the NV center is a particularly interesting probe is that you have this ability to choose a distance away from your system. So this has direct implications in applications towards these nice scanning NV measurements that several groups have. Okay, so I didn't have time to talk about a lot of the other efforts in my group in improving shallow NV centers, but I'll just point you to a few efforts and papers. One thing that we discovered is that in addition to the spin coherence time of shallow NV centers being affected by the surface, we also see that the charge dynamics are strongly affected and that this has consequences for the ODESR contrast. This paper is on the archive right now. As I alluded to during some of the questions earlier, we have also been trying to come up with new ways to functionalize the diamond surface. And one of the challenges is that when you keep on taking your diamond out of, you know, out of chambers and into atmosphere, you always get a layer of adsorbates on the surface. So in order to avoid that, what you need is some way of doing in situ processing, and then you have to keep it under a UHV environment to stop a monolayer of stuff from forming on the surface. So we have recently built an ultra-high vacuum cluster tool, which has a big surface spectroscopy and processing chamber with an attached UHV cryogenic confocal microscope. Here are some actual, you know, images of NV centers in this UHV cryogenic confocal microscope, which is really exciting. As far as I know, this is the first time anyone has worked out high NA imaging in UHV. So this has been kind of a big technical challenge over the last few years. And then in parallel, what we've decided to do is start kind of revisiting this question of whether or not it's possible to do just sort of normal conventional wet chemistry at the diamond surface. Normally, this is quite hard to do because diamond is inert and it has this really tight lattice constant. So doing kind of conventional wet chemistry with high yield is generally thought to be impossible. But what we discovered is that there's this brand new class of catalysts that have been developed by the synthetic organic community over the last decade or so called photoredox catalysts, where you get very different catalytic behavior just by shining blue LEDs basically on your catalyst. And the epicenter for this research is at Princeton. So we started a collaboration with Rob Knowles's group down in chemistry to try to apply this to the diamond surface, and have set up sort of a reaction discovery pipeline involving this X-ray spectroscopy and then, you know, in careful surface preparation. And we actually do have some really exciting preliminary hits where we're able to make fluorine terminated diamond with this ambient, you know, condition wet chemistry. And we've found that actually this catalysis is very general, and we've been able to make a few other surface terminations as well. Okay, so with the last 7 or 8 minutes or so, I'd like to completely switch gears and give you, oh, I think someone has a question.
Yes, Stuart?
Yes. I have a question. Thanks, Nathalie, already for the interesting talk. I was wondering a little bit about what you told about this DIR measurement you did. This DIR allows you to specifically couple to certain spins on the resonance frequency of the pulse you apply in this DIR sequence.
Mm-hmm.
And as far as I understood, you fixed this frequency in the DIR sequence, which means you specifically couple to, let's say, only one type of spins you investigate. By what means did you choose this frequency? And did you also look at other frequencies and thereby other sort of spins that could cause decoherence?
Yeah, so I mean, these measurements always start with spectroscopy. So we just sweep the frequency of this tone and then see what's there. But the tone that we ended up using here, or the signature that a lot of people see, is just S equals a half, G equals 2. So it's selective, but the vast majority of electronic spin defects are also going to be G equals 2, S equals a half. So it could be that we're still addressing, several different populations that are heterogeneous. But I guess I can tell you, we don't see any obvious hyperfine peaks associated with it. So we know that they're like not nitrogen containing defects. But other people have done, deer spectroscopy in heavily nitrogen doped samples where you can clearly see that you're looking at something with nitrogen, for example.
Cool, thank you.
Oh no, that's the same hand. Okay. So, okay, just in the last few minutes, I thought I would share sort of another story that is a completely different kind of system from what I've been talking about so far. So hopefully I've convinced you that this is a generally powerful approach, correlating surface spectroscopy measurements with qubit measurements to figure out what's going on in these systems. So what we started doing about a year ago now was trying to use the same exact approach to improve superconducting qubits as well. So probably many of you have seen plots like this, where this is basically the superconducting qubit lifetime and coherence time over time. So it's sort of like a Moore's law plot. I think for a while people were calling it Shulkoff's law, but then Rob doesn't like that because one of the things that a lot of people don't talk about so much is that this plot has sort of stagnated over the last 7 or 8 years. So there was a lot of impressive improvements from the late 90s to about 2012. And the last time someone improved the 2D transmon was in 2012 when they hit around 100 microseconds. So improvements since then have involved basically looking at the lifetime of a microwave excitation in a very large cavity, but the actual qubit coherence time has been kind of stuck around this level for quite a long time. So what we asked was whether or not we could learn anything about the surface and then use that for systematic improvements. And we actually had these preliminary measurements on state-of-the-art IBM qubits that we had gotten in collaboration with Pat Gumman at IBM as part of an NSF team that we're on. And we just did some preliminary X-ray photoelectron spectroscopy. And what we saw, I thought we were going to see, some different surface states and particular contaminants that we could get rid of, but actually all that we saw was carbon and oxygen. We couldn't even see through to the silicon or aluminum, which means that these things are covered with such a thick layer of adventitious carbon or fabrication residue that we didn't even have access to the surface. So this had to be at least 10 nanometers thick. And just to give you a sense of the kinds of losses that we're talking about, if you just had a surface participation ratio of something like a part per million, then just a few nanometer layer of PMMA is lossy enough to account for the kinds of limiting cues that people see in these resonators. So this contamination is a serious problem. So in collaboration with Andrew Houck's group, we decided to take a look at what we could do in terms of improving the fabrication and material system for 2D transmons. So just to orient you, what the Houck group generally uses is Josephson junctions that are made out of aluminum, and then the capacitors and resonators are all made out of niobium, and this is fabricated on top of a sapphire substrate. So the first thing that we did was looked at what was going on with the substrate. And in fact, the sort of as received sapphire substrates that we get from the company have quite a bit of contamination at the surface. So even just looking at AFM, you can see that there's a lot of little dots everywhere. And they generally don't get removed with just sort of conventional solvent cleaning. So we just applied a lot of kind of aggressive acid cleaning and also some very gentle wet etches of the sapphire surface, and we can now get these very smooth and clean sapphire substrates. Additionally, we can do this X-ray spectroscopy to see if there are any heteroatom contaminants, and what we found is that there was processing that left a bunch of zinc contamination at the surface. And we could, and this was very, very difficult to remove. And what we found is that what we developed was an isotropic wet etch that removes the top few nanometers of material, and that seems to get rid of this heteroatom contamination. Finally, we can do high temperature annealing in air, and then that recovers a surface where you can actually see these step edges in AFM. So we have close to atomically smooth sapphire surfaces. So using these really nice substrates, we then kind of trained our eye on, well, what can we actually replace about the material system itself? And one of the things that Bob Kava kind of immediately pointed out when we started this project was like, why the heck are you guys using niobium? Niobium has the worst oxides in the world. You get all of these really weird substoichiometries, and probably a lot of these are lossy in the microwaves. So his suggestion was to replace with tantalum, which should have much better behaved oxides. So the tricky thing about tantalum is that if you try to grow thin films of tantalum, you actually get the very low TC phase of tantalum, which would be not great for a variety of reasons. But fortunately, Dan Prober's group at Yale had actually figured out in the 90s that you can stabilize the correct bulk phase in thin films by high temperature sputtering. And this is now just commercially available from companies from foundry services that do sputtering. So what we can do is now grow BCC phase tantalum on top of these nice sapphire substrates. And then if we look at these substrates and we look very carefully at the oxide layer, we can indeed verify that we get this very well behaved stoichiometric oxide as Bob predicted. We see that it's basically 2 to 3 nanometers, no matter what we do to these films. It's very, very robust. It's almost like aluminum oxide where you have this kinetically limited film thickness, and sort of no matter what processing we put it through, we always have this 3 nanometer oxide. Okay, so the end result of all of that materials work is that now compared to the niobium qubits that Andrew Hauk's group was making, which were not as good as the absolute state of the art, we have been able to extend the T1 of these transponds by about a factor of 10. So our kind of typical best now is a T1 of around 300 microseconds, which beats this previous record by a factor of a few. And this was just a very, very simple kind of material change from niobium to tantalum. In addition to that, we can get T2s of around half a millisecond through dynamical decoupling. And just to show you that we're not cherry picking the data, one of the things that's often hidden under the hood of these experiments is that there's actually variations in time for T1 and T2 of these qubits. So here's a time sequence where the T1 is relatively stable around 300 to 400 microseconds, and the T2 varies a little bit more, but it's still sort of comfortably always over 200 microseconds. Okay. So basically, we have found that replacing niobium with tantalum improves every type of qubit we've tried, sort of regardless of surface participation ratio and geometry. And now we're working to systematically study how various material properties affect T1 and T2, like the grain size of the tantalum, the oxide thickness, and stoichiometry. And we're also working to remove sort of this last layer of adventitious carbon and other contaminants at the surface. And then the other thing that I'm kind of interested in is this time variation in T1 and T2 is pretty weird. There's been some recent work where people have some evidence that this is related to cosmic rays, but I think that this could be a really interesting, area of exploration for looking at the constituent materials. Okay. So the shallow and V-center work that I talked about was primarily led by Peace Sangtuezen, who is now on faculty in Thailand, and Bo Dwyer, who is a graduate student in the Lucan group, who I started collaborating with when I was still a postdoc there. This recent surface spin story that I told you about is a collaboration between my group and Misha's group, and that was led by Bo again, and Leela Rogers in my group, and Alana Urbach. And we've really had a fun time all analyzing this data together. I should specifically mention that Dolev Bluestein was really enthusiastic about going back and reanalyzing this data and kind of drove a lot of this effort. The superconducting qubit work was led by Alex Place and Leila Rogers, and was in collaboration with Bob Kava and Andrew Hauk's group. And then I have a number of collaborators and funding sources to thank, so I'll just leave this slide up while I take questions. Thanks.
All right, thank you, everyone. You can, I think Zoom has a clap feature for those who are interested. Thanks for the great talk, and we open to questions, so please raise your hand if you have a question. I think I see Anton already has one, is that correct?
Yeah, that is correct. First of all, I find the tantalum story absolutely fascinating, especially given how long people have been trying to work with transmons, and it's not like everyone is happy with the awesome coherence times. But so, do you know what is limiting the coherence times in tantalum qubits now?
So we do not know. In particular, well, okay, I would say that nobody knows what's limiting their coherence times in general. So you know, we don't have, there's a long list of candidate microscopic mechanisms, but we don't know yet. One thing that we're kind of discovering in particular is that, right, a lot of our packaging and you know, basically the way that the Hauk lab had built up their setups was for a world where your coherence times are only like 50 microseconds. So now there are a lot of things that suddenly matter that you didn't have to worry about at all previously. So I think there's probably some amount of microwave hygiene, thermal management kind of stuff that we need to now focus on for a little while. But yeah, it would be really interesting to figure out whether or not this remaining oxide is a huge problem. There are not really good microwave loss measurements of tantalum oxide, especially at low temperature and low power. So we don't actually know how much that is affecting us. And then, of course, there are quite a few people who believe that quasi-particles play a really big role in T2, and we don't know, you know, whether or not you would expect there to be an improvement from tantalum or not.
Thanks.
Great. I think we have a question from Jennifer Choi.
Hi, Nathalie. Thanks a lot for the great talk. I have a question about the potential etching of diamond during the various treatment steps. Do you have any concern over etching during both the Triassic clean as well as oxidation? And in the experiments where you repeated treatments on the surface, do you notice any changes in the depth of the NV centers?
Yeah, so that kind of cycling where we go through repeated treatments, we do not see any changes in the depth within our error bars, and we definitely don't see that they're systematically getting shallower or anything. So I think we really are just kind of affecting this last layer with this last bit of oxygen annealing. But I should warn you, that process is a little bit on a knife edge. So if you just increase the temperature by 5 degrees, then you expect there to be kind of significant etching of the diamond surface, because you should eventually start to burn in atmosphere. Acid cleaning and these other kinds of processes shouldn't really etch any material away. The only thing that we do that intentionally removes material, other than of course reactive ion etching, is that we do this vacuum annealing step in intentionally kind of bad vacuum so that we can graphitize the top few nanometers of material, and then we acid etch that graphitic carbon away.
Thank you.
I have a question. So earlier you were motivating this sort of mobile surface spins in the part 2. Do you have a sense for the density of these things on the surface? Like, what is the surface coverage of those mobile things?
Sorry, I think the audio froze for just a little bit. It's probably my internet's fault, so I missed your last
Sure,
sentence.
I can repeat. Yeah, the question. Yeah, I'm wondering about the density of these mobile surface spins. Like, what is the typical surface coverage? Are you able to infer that? from
Yeah. So I mean, so it still does come from this the scaling with depth. So as long as you only fit to the deepest NVs, you should still be able to back out the density, and that's where we get this whatever it was that I said 0.005 per nanometer squared. This roughly like 14 nanometer linear spacing.
I see, 14 nanometers. Okay, great. Are there any further questions from the audience? We have one from Babak.
Yeah, so when you were showing this analysis with the log of log on a log scale, log, there was a lot of choppiness to your data.
Mm-hmm.
And I guess this comes from some additional time dependence that you have there, and taking a log of a log creates that. Do you understand where that? Is that the case, and do you understand where that comes from?
Yeah, so I guess I wouldn't call it choppy as much as noisy.
Noisy.
Which
Okay.
is a little
Are these
bit
error
different.
bars, or are these?
Yeah, these are error bars.
I
so
see,
the black,
okay.
We should probably pick a different color scheme. But the black is the data points, and then the blue is the error bars. So the reason that the error bars are large to begin with is because, so if I go to the deer, right. So the way that we take this data is we take a Hahn echo, and then we take a deer echo, right? And then our signal is this divided by this. So if these two curves are very close together, then you have very large error bars.
Right.
So at the beginning of the decoherence, you have large error bars, and then at the end, you don't have any signal left, so you have large error bars again.
Okay, understood. Thank you.
I guess I have one final question regarding the superconducting qubit work. So you stuck with the junction as being aluminum, but you did have to make contact to it, which means that you are putting aluminum on tantalum. Mm-hmm. Which also suggests that perhaps you could make a junction there. Have you tried that?
So we've spent some time thinking about this because, if you can make a good tantalum oxide, it seems like you should be able to make a good Josephson junction. I think the real challenge is this high temperature sputtering. Because to get the right phase of tantalum, you need to sputter at, 700, 800 degrees. Then it is hard to see how you can do, basically you don't have an E-beam resist that will survive those temperatures. So I don't really know how to make a good junction that way.
Sure.
A good small junction.
Right. I guess I was actually imagining a one side maybe perhaps remaining as aluminum.
Oh, I see. Yeah, I guess that is possible.
Okay.
Probably.
Yeah, if the in-situ oxidation is still okay.
Yeah.
Okay, so I think that covers. I think that there are no further questions. As Babak has pointed out in the chat, the registration for the next colloquium in 2 weeks by Titus Newport is open. And before I close, I'd like to thank Nathalie again for coming and giving this great seminar. And I'll look forward to seeing everyone next week.
Thank you.
2 weeks, excuse me. Thanks again, Nathalie.
Thanks, Nathalie.
Thanks.